Think about your workspace after a long day. You might have documents, stationery, or other items scattered around. To quickly locate what you need, it's much easier when everything is organized and in its proper place, right? While sorting algorithms can't organize your physical workspace, they can perform a similar function for data. They streamline the process of finding and using necessary information quickly, which is particularly valuable for organizations developing efficient applications. Sorting algorithms act as a set of instructions that organize information in a precise and efficient order. When data is sorted, whether it's numbers, words, or objects, it is arranged in a sequence, such as from smallest to largest, or alphabetically. This is important because sorted data is easier to manage, search, and analyze. In this video, you will learn how sorting works, how it helps solve problems more efficiently, and how it applies to everyday life and computing. Sorting is a fundamental concept because it helps in organizing information. This is extremely valuable because data needs to be accessed and used effectively. Let's imagine a few scenarios where sorting makes life easier. Take a library, for example. Books are typically organized by the author's last name, genre, or title, making it easy to find what you're looking for. If the books were placed randomly on the shelves, finding a specific one would take much longer, leading to less effective learning. Your phone's contact list is another great example. Typically, contacts are sorted alphabetically, making it easy to scroll and find the person you want to call or text. Now, if the contacts were in a random order, locating a specific name would be frustrating and time-consuming. And if you've enjoyed a seamless online shopping experience, you can thank sorting algorithms. They allow you to sort items by price, customer ratings, or popularity, helping you find the products that best suit your needs. For example, if you're searching for the most affordable option, you can easily sort items from lowest to highest price. As a final example, educators and administrators often sort students' grades from highest to lowest. This makes it easy to review individual performance relative to others and identify trends across the class. Sorting isn't just about convenience, it's about efficiency. In computers, sorting is crucial because it makes searching and organizing data much faster. If you have a list of thousands of names and you need to find one specific name, a sorted list allows the computer to find it quickly without having to check every single name. That's time-saving and valuable. But how do they work exactly? Simply put, sorting algorithms are the step-by-step methods computers use to organize data. Once organized, the data can be accessed or edited quickly and easily. Each algorithm uses a unique technique for sorting. So let's look at some of the most popular ones to understand how they work. For example, bubble sort is one of the simplest sorting algorithms. Imagine you want to sort a deck of playing cards based on the number of the card. A bubble sort algorithm starts by comparing the first two cards. If the first card is larger than the second, it swaps and reorders them. It then moves to the next pair. This process is repeated until all the cards are arranged from smallest to largest. And as it continues with new entries, smaller cards move or bubble to their place in the order. Bubble sort algorithms are used in applications where simplicity and ease of implementation are essential. Their ease of understanding and implementation makes them particularly useful for small datasets or when the dataset is nearly sorted. Another key sorting method is selection sort. It works in sequence by finding the smallest number in a list and moving it to the front. Then it looks for the next smallest number and places it next in line. A selection sorting algorithm starts by picking out the card with the lowest value and moving it to the leftmost position. Then it looks for the next lowest card and places it right after the first one. The process continues until all the cards are arranged from lowest to highest value. Selection sort algorithms are ideal for situations where memory usage is a concern because they minimize the number of swaps. They're particularly useful in scenarios where the dataset is relatively small or where simplicity and predictability in performance are more important than speed. Another useful method is the insertion sort, which organizes data by gradually building a sorted list. inserting each new element into its correct position. If the algorithm starts with one entry and then another comes along, Insertion Sort places the new entry in its correct position relative to the first. It keeps adding incoming entries one by one, placing each in the right spot until your list is fully organized. With Insertion Sort, the algorithm takes each value or number from an unsorted list and inserts it into its proper place within a growing ordered list. This process is repeated until the entire list is sorted. Insertion sort algorithms are particularly effective for small or partially sorted datasets. Its simplicity and efficiency make it ideal for real-time applications with limited computational resources, such as embedded systems or manual data entry. Apart from bubble, selection, and insertion sorts, there are many more sorting algorithms worth experimenting with, each with their own strengths and unique applications. The bucket sort groups elements into buckets before sorting. Merge sort divides the list and merges the sorted parts. Radix sort processes numbers by each digit, useful for sorting large numbers or data with a significant range of values. And quicksort is known for its efficiency in partitioning and sorting segments. Sorting algorithms are widely used in real-world applications, playing a crucial role in organizing and processing data across various fields. From social media fields that sort content by recency, or engagement to music streaming services like Spotify that help you discover your next favorite song, these algorithms are integral to our daily digital experiences. Whether it's sorting names, numbers, products, or posts, these algorithms are at the core of many everyday tasks and computer processes. In this video, you learned how key sorting algorithms work, why they're efficient, and how crucial they are to solving real-world challenges. If you understand sorting, you can better grasp how computers solve problems and organize information. This gives you the critical insight to optimize data processing and improve decision-making in any application you choose to develop. You walk into a library and find all the books on a shelf in disarray, some tall and some short, randomly placed. You've been asked to organize them by height, from the shortest to the tallest. Arranging these books neatly not only makes the shelf look tidy, but also makes it easier to find books in the future. In this video, you will learn how to use the bubble sort method to sort items effectively, just like organizing books in a library. Looking at the shelf, you notice the books are in random order. You aim to arrange them so the shortest book is on the left side of the shelf and the tallest book is on the right. This task is similar to sorting data. You will use the bubble sort method, a straightforward approach perfect for small data sets. You begin by comparing the first two books. If the first book is taller than the second, swap their positions, placing the shorter one on the left. Then, compare the second book with the third. If no swap is needed, you will move to the next pair. Keep swapping until you reach the last element. This is known as the first pass. By this first pass, the tallest book will have bubbled up to the end of the row. This mirrors how bubble sort works in programming, iteratively comparing and swapping items to sort a list. With the tallest book in the correct position, repeat the process for the remaining books, known as a pass, ignoring the last one because it's already in its proper spot. You start again from the first book, comparing and swapping if needed. With each pass, the next tallest book moves to its correct position. This process gradually sorts all the books until the shortest is on the far left and the tallest on the far right. You continue repeating the sorting process, each time considering one less book. Eventually, no more swaps are needed, and the books are perfectly sorted from shortest to tallest. So what reflections can you draw from this example? The bubble sort algorithm made the task simple. It required no complex thinking, only comparing and swapping as needed. While it may take longer with more books, bubble sorting is easy to implement for small data collections. Now let's take this into Java and translate the sorting method into code. First, create the main class to start coding. Define an array of integers representing the height of each book in centimeters. Next, the modularity of the code can be enhanced by segregating the frequently used methods. For instance, you'll print the array twice, that is, before and after the sorting. Writing a dedicated method that handles printing the array elements is better, which you can call from the main method function whenever needed. Now you need to call this method to print the array from the main method. This is where the magic of sorting happens. You have to write a separate method to execute the sorting, which is as follows. Name the method as bubble sort and pass on the array. Then call the method from the main method. Now that you have sorted the array, you need to print and check if the array element has been sorted. Here you again need to call the printHeight method to print the sorted array from the main method. Once you run your program, you'll have the following output, which lists the books in height from shortest at 12 centimeters to tallest at 15 centimeters. Great job! You now know how to use the bubble sort method in Java, which allows smaller elements to bubble up to the correct position through repeated comparisons and swaps. While it's simple and easy to understand, you also discovered that it might not be the most efficient choice for larger datasets. However, it's a great way to get started with sorting algorithms. It provides valuable insights into how sorting works and can be applied in everyday situations like organizing a bookshelf. Tony invited his friends over for a card game. He was dealt a hand of shuffled cards and wants to sort them in ascending order, from the lowest to the highest value. You can sort cards based on the card value or the suit. Tony decides to sort the cards based on the card or number value. Therefore, the number 2 is ranked the lowest and 10 is the highest. A card with the lowest value is 2 and an ace has the highest value. Can you write a Java program to help Tony sort his cards? In this video, you'll learn how to apply the insertion sort algorithm, simulating how people arrange cards based on card number ranking. The pack of cards only contains number cards. First, let's view Tony's initial hand. He has 5 cards, 7 of spades, 3 of diamonds, 10 of clubs, 5 of hearts, and 2 of spades. Sorting the cards by hand requires Tony to pick up a card and place it in the correct position relative to the first card on the left. He will continue this process until all the cards are sorted. Tony starts by considering the first card, the 7 of spades. Since it's the only card, it's already sorted, so no action is needed. The second card is the 3 of diamonds, which is smaller than the 7 of spades. Tony moves the 3 of diamonds to the left of the 7 of spades. His hand is now 3 of diamonds, 7 of spades, 10 of clubs, 5 of hearts, and 2 of spades. The third card is the 10 of clubs, ranked higher than the 7 of spades. Therefore, the card is in the correct position and no sorting is needed. The fourth card is the 5 of hearts. 5 is smaller than 10 and 7 but greater than 3. Therefore, Tony inserts the 5 of hearts between the 3 of diamonds and the 7 of spades. The last card is the 2 of spades. 2 is smaller than 3 and Tony moves the card to the left of the 3 of diamonds. His hand is now sorted from lowest to highest, as the 2 of spades, 3 of diamonds, 5 of hearts, 7 of spades, and 10 of clubs. How does this relate to a Java program? The insertion sort algorithm can simulate the sorting of the cards. Navigate to IntelliJ to explore the insertion sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the numbers on the cards. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The insertion sort method will sort the card values in ascending order. Insert another printArray to view the sorted cards. Step 2. Insert a printArray method consisting of a for loop to iterate over each element in the cards array. The cards variable represents each card value during each iteration. The print method will indicate each card value followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it Insertion Sort. This method has a for loop that starts from the second element, index 1, and iterates through each element in the array. The purpose of this loop is to pick each card one by one and place it in its correct position relative to the already sorted part of the array. The current card variable stores the value of the current element that needs to be placed in the correct position. Next, insert a while loop as an inner loop. This loop checks if the current element is smaller than the elements in the sorted part of the array from the left side. If so, it shifts the larger elements one position to the right to make space for current card. Therefore, cards counter 2 plus 1 equals cards counter 2, indicates the larger elements are shifted from one position to the right. The counter 2 indicates the decrementing counter and checks the next element on the left. After finding the correct position, the current card is inserted into its appropriate position within the sorted portion of the array. Step 4. Let's view the output. Java sorted the cards just like Tony did. In this video, you learned that the insertion sort method simulated how Tony sorted his cards by placing each new item in the correct position relative to the other cards. Although insertion sort might not be the fastest algorithm for large datasets, it is highly effective and easy to understand for smaller or nearly sorted lists, making it a perfect choice for Tony's task of organizing his hand of cards. Have you played a game where you have to sort items based on size, color, or value? Many games advertise that sorting items can increase your IQ, as it keeps your brain active. Ashley has 5 coins of different sizes and wants to arrange them from smallest to largest. The diameters of the coins are 25, 15, 30, 20, and 10. Can you help Ashley write a Java program that can sort the coins? In this video, you'll learn how to apply the selection sort algorithm, simulating how people arrange coins based on size. First, let's look at how Ashley will sort the coins by hand. She randomly places the coins on a table. The order, based on diameter in millimeters, is 25, 15, 30, 20, and 10. Ashley picks up the smallest coin, the 10 millimeters, and swaps it with the first coin, the 25 millimeter. The order of coins is now 10, 15, 30, 20, and 25. The smallest coin is in the correct position. Next, she looks at the remaining coins and selects the 15mm one as the smallest. Ashley notices that the coin is in the correct position, so swapping coins is unnecessary. The last 3 coins are 30, 20, and 25. Ashley selects the 20mm coin and swaps it with the 30mm coin, so the order of the coins is now 10, 15, 20, 30, and 25. Lastly, she swaps the 30mm with the 25mm. The order of the coins is now 10, 15, 20, 25, and 30. Ashley has sorted the coins from smallest to largest based on their diameter. How does this relate to a Java program? You can use the selection sort algorithm to simulate the sorting of the coins. The algorithm will split the list into 2 groups, a sorted group to the left and an unsorted group to the right. Similarly to what Ashley did, the algorithm will take the smallest size from the unsorted group and place it in the sorted group. When all the coins are sorted, the algorithm will stop. Navigate to IntelliJ to explore the selection sort algorithm in 4 steps. Step 1. You have to create the main class and define an array of integers to store the size of the coins in millimeter. Call the printArray method to display the initial array. You can then compare the before and after sort outputs. The selection sort method will sort the coin sizes in ascending order. Insertion of the printArray to view the sorted cards. Step 2. Insert a printArray method consisting of a for loop to iterate over each element in the sizes array. The sizes variable represents each coin size during each iteration. The print method will indicate each coin size followed by a space for readability. Outside the for loop, insert a print line statement to view the output on a new line. Step 3. Insert another method and call it selection sort. The length of the sizes array is stored in the variable named length. The for loop starts from the first element, index 0, and iterates through each element in the array up to the last element, or length -1. This ensures that the outer loop controls the boundary between the sorted and unsorted groups of the array. After each iteration, one more element is added to the sorted group. The algorithm initially assumes that the first element in the unsorted portion, or counter, is the smallest. The index of this element is stored in min index. The inner loop will start from the element right after the counter and go to the end of the array. The if statement compares each element in the unsorted group with the current minimum. If a smaller element is found, the min index is updated to this new index as indicated by the new counter. The smallest element, found in the unsorted group, located at min index, is then swapped with the first unsorted element, located at counter. The value at sizes, min index, is then temporarily stored in temp and replaced with the element at sizes, counter. Lastly, this element is then stored in temp. The outer loop continues, moving the boundary between the sorted and unsorted groups to the right, one by one, after each iteration until the entire array is sorted. Step 4. Let's view the output. Java sorted the coins just like Ashley did. In this video, you learned that the selection sort method simulated how Ashley sorted her coins. The algorithm repeatedly scanned the unsorted portion of the list to find the smallest element. Although selection sort is easy to interpret and implement, it is not the most efficient algorithm for large data sets. However, its simplicity makes it an excellent choice for small lists or when an easy-to-implement sorting method is needed. Sorting is an essential process in programming. It allows you to organize, prioritize, retrieve, and make sense of information and processes. With sorting, you can also group data for problem solving, optimization, and further processing. There are 3 basic Java sorting algorithms: bubble, insertion, and selection sort. With bubble sort, each element is compared with its adjacent element, and if they are in the wrong order, they're swapped. This process is repeated iteratively until the list is sorted. Insertion sort divides the list into a sorted and unsorted group. An element is taken from the unsorted group and placed in the correct position of the sorted group. This process is repeated until all the elements are sorted. Selection sort selects the smallest element from the unsorted group and moves it into its correct position of the sorted portion. This process is repeated until all the elements are sorted. In this video, you'll compare the 3 algorithms based on time efficiency, complexity, and use cases. Understanding time complexity helps you choose the most efficient sorting algorithm based on the size and nature of the data you're working with. Time complexity indicates an algorithm's time to run with large or complex data sets. In the context of Java sorting algorithms, time complexity describes the efficiency of different sorting methods. Time complexity is described with the big O notation, or big O of n. It provides an upper bound on the growth rate of an algorithm's running time, or memory usage, as the size of the input data increases. The n indicates the size of the input data, or the number of elements in an array. The big O of n denotes a linear relationship between the input size and the time required to process that input, making it straightforward and predictable regarding time complexity. You need to know all 3 algorithms' best and worst case scenarios. Let's explore examples of best and worst case time complexity for the 3 sorting algorithms. The selection sort has the highest time complexity for 5 elements, making it the least preferred option. Let's start with bubble sort. Big O of n denoted the best case scenario, indicating that the list is already sorted and no swaps are needed. For the worst case scenario, the list is sorted in reverse order. Therefore, each element is out of place. Bubble sort will require n-1 passes through the list, with each pass making approximately n comparisons. Therefore, the number of operations is proportional to n multiplied by n-1 divided by 2, simplifying to big O of n squared. In practice, even in a best-case scenario, most implementations of bubble sort still perform big O of n squared operations unless optimized with a flag to stop early. It's important to note that bubble sort is rarely used in practice due to its generally poor performance, even with the early termination optimization. So, why perform big O of n squared operations? The nested loop structure of bubble sort, where one loop controls the number of passes and the inner loop performs the comparisons, leads to a quadratic time complexity of big O of n squared. This means that if the input size doubles, the time taken increases 4 times. The second algorithm is the insertion sort. O of n denotes the best case scenario, as the list is nearly sorted. Each new element is placed directly after the previous one, requiring only one comparison per element, and the number of operations is linear. In the worst case scenario, each element must be compared with all the previously sorted elements, leading to n comparisons for each insertion. This results in big O of n squared time complexity. Similar to bubble sort, insertion sort has a nested loop structure. The outer loop iterates over the elements, and the inner loop compares and shifts elements to find the correct position, leading to a quadratic time complexity. The third algorithm is the selection sort. Interestingly, selection sort always scans the entire unsorted portion of the list to find the smallest element, regardless of whether the list is already sorted. Therefore, time complexity is always big O of n squared. The algorithm makes n comparisons in each pass to find the minimum element. Since this process is repeated for each element in the list, the total number of comparisons leads to a quadratic time complexity. Let's review the time complexity of the 3 algorithms. Big O of n indicates a linear time complexity as time grows linear to the input size. This is the best case scenario for bubble sort and insertion sort, where the list is nearly sorted. Big O of n squared indicates a quadratic time complexity with time that grows quadratically as the input size increases. This occurs when the list is not sorted and the algorithm must perform many comparisons, swaps, or shifts. In this video, you compare the time complexity of the 3 basic Java sorting algorithms. Understanding time complexity helps in choosing the correct algorithm based on the nature and size of the data, allowing for more efficient sorting in practical applications. Insertion sort is often the best choice for small or nearly sorted datasets because it can perform close to big O of n. Bubble sort is also effective for nearly sorted lists, though it is generally slower than insertion sort due to more comparisons and swaps. Selection sort is straightforward, but consistently slower with the time complexity of big O of n squared, regardless of the dataset's initial order. Happy coding!